Let us have a look about what is it like inside a nuclear reactor.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump.
So now that we have discussed what's all about a reactor, let's discuss some type of reactors. The first is LWR or light water reactors. in which the neutron moderator is light water. The first one is pressurized water reactor, in which a pressurized chamber of water is used. This is the earliest, which is why it is the most. We had discussed this earlier, that the largest number of reactors on the planet are pressurized water reactors. In this, the coolant and the neutron moderator are both water. It's more stable. The disadvantages are that because of the high pressure, you need strong piping and other strong equipment, which makes it expensive, and it cannot be refueled during operations. Another one is supercritical water cooled reactor, in which the water is used in its supercritical phase, which is around 374 degrees Celsius and 22.1 megapascal pressure. The properties of water are completely different in this range, and it offers a very high thermal efficiency, and there are some reactors which work on this principle. Another one is boiling water reactor, in which the water boils. It's not on as high pressure as the pressurized water reactor is, but it has water boiling and the pressure is normal. Now the point is that it is not much stable, does not offer much efficiency, but it's much cheaper and it can be refueled during operation. So every reactor has its own advantages and disadvantages. There's also another way, which is called light water graphite reactor, in which the moderator is light water but the control rods are made of graphite instead of boron and cadmium. This is another type of reactor. And there is a pressurized heavy water reactor, which is similar to the pressurized light water reactor, just that the moderator is heavy water instead of light water. A type of reactor not known to many people are the molten salt reactors. In this, the reactant and or coolant are both or any one of them is a molten nuclear salt, like a chloride or a fluoride of some particular element like uranium or thorium. It was initially developed in the 1950s, way back decades ago, and it offered higher efficiencies because all of the states were molten, so which means the temperature was high enough. So things like activation energy and thermodynamic factors were quite favorable to offer higher efficiencies. There were lower risks because since everything was molten, things could be controlled very easily in times, 8 times if something went wrong. The attacks would have been potentially lower because an attack meant that the entire molten salt would start flowing. So the attacks would have been potentially lower and it would have generated lesser waste. However, for historic reasons, this reactor was never deployed.
Let's have a look on nuclear power and climate change.
In the 2015 Paris Agreement, world leaders agreed on firm targets to fight climate change. The aim is to limit the increase of global average temperatures to well below 2 degrees centigrade. This is the threshold at which the worst impacts from climate change can still be avoided. The challenge is immense. Today, 70% of electricity comes from burning fossil fuels, but by 2050, around 80% of electricity will need to be low carbon. Fighting climate change while still meeting development goals requires a radical transformation of energy production and usage. Is nuclear power a suitable option to address climate change mitigation? Over their entire life cycle, water, nuclear and wind power sources are the lowest emitters of greenhouse gases. During operation, nuclear energy does not emit any greenhouse gases. Its carbon emissions come primarily from the mining and enrichment of uranium. Today, nuclear power helps avoid over 2 billion tonnes of CO2 emissions per year. That's the equivalent of taking more than 400 million cars off the road every year. And compared to wind and solar, nuclear requires significantly less land to generate the same amount of electricity. New, innovative reactors now being built also have the potential to significantly increase the sustainability of nuclear power. They can produce 60 to 70 times more energy per kilogram of uranium than with current technologies. All low-carbon energy sources are crucial for meeting climate change goals. However, wind and solar cannot provide energy continuously, 24/7. They need a backup energy source, and this mostly comes from fossil fuels. Maximum use of renewables can be achieved through energy storage, adjusted demand, or help from other flexible energy sources. Complementing renewables, nuclear can contribute to the transition to a low-carbon economy, helping reach climate change targets.
An important process with respect to old nuclear reactors or nuclear reactors which are no more functional is decommissioning. Now, what's decommissioning? It consists of dismantling. Basically, the entire nuclear plant is dismantled to its component parts, right to concrete and steel. Now, this consists of a lot of nuclear waste. In fact, almost the entire nuclear plant consists of nuclear waste, either HLW or ILW or LLW. And all of this has to be taken care of according to the jurisdiction of the place and the technical problems that could be generated by the nuclear waste. So some waste could be incinerated, some could be buried in shallow landfills, some might be buried in deep landfills. In fact, an interesting example is that the entire water from the nuclear power plant has to be put into landfills for centuries to come. You also have decommissioning funds. So any nuclear plant, when it's first made, there is a decommissioning fund allotted to it. What happens in this fund is that we realize that in a few years, maybe in 20 or 25 years, this nuclear plant has to be decommissioned, and for this the fund is generated right from day one. Now there are three terms: inactive reactor, shutdown reactor, and decommissioned reactor. Inactive reactor is basically reactor which is right now inactive. It's not processing, it's not generating energy, but if nuclear fuel is given and maybe some maintenance is done, it can again start reacting. A shutdown reactor is basically when the reactor core or something has malfunctioned, or maybe they have stopped using it in such a way that the reactor cannot be further used. And the decommissioned reactor is in such a way that the entire plant is dismantled and decommissioned, which basically means that the land is fresh as new. Over the land where earlier the plant was present, you can in fact start new construction. This is the difference between inactive, shutdown, and decommissioned reactor. A disastrous use of atomic energy is in the process of making a hydrogen bomb. Now, this is a Teller-Ulam two-stage thermonuclear bomb design, which is a type of a hydrogen bomb. In this, you can find that there is going to be rapid chain reaction initiation. Basically, there is a chemical core which is controlled by electronic or mechanical means. And once there is an explosion in this chemical core, it makes the fission fuel to start reacting. This gives rise to a lot of X-rays which are released as a form of the energy, and this starts forming a plasma in the polystyrene foam, which is a kind of covering to both the fission and the fusion reactors. And there is obviously a casing which ensures that the X-rays are reflected internally, and this is basically the fusion fuel with a fission spark plug. So basically this process works in such a way that the X-rays approach here, this fissionable spark plug starts fissioning because of the energy received, and suddenly there is a lot of energy formed and the fusion fuel starts to fuse. So basically fusion needs a lot of energy to initiate. We'll have a look on it in a short time. And because of that, this fusion fuel starts to react and it produces a massive amount of energy, which is why it bursts, and it's a disastrous explosion, and we know which is why it's called a hydrogen bomb. Let's have a look on radioactive disasters. So radioactive disasters have occurred time and again. Incidents such as Fukushima Daiichi disaster, which occurred in Japan, and Chernobyl nuclear disaster, which occurred in Russia, have been rated 7 on the international nuclear event scale. There have been several other disasters as well. 3 Mile Island, Shitem disaster are some notable examples, mostly each of reactor meltdown. Lake Karachay was a prominent case of commoners being affected by nuclear waste disposal. This is a lake in Russia in which nuclear waste was being disposed and commoners were affected by this. This is the INES, or the International Nuclear Event Scale, according to which any radioactive disaster is judged. And as we can see, 7 is a major accident, is the highest level on which Fukushima Daiichi disaster and Chernobyl nuclear disaster have been rated. An important aspect of nuclear power is attacks and concerns on nuclear plants themselves. Obviously, terrorists can use nuclear power for inhuman activities and whatnot. However, attacks on nuclear plants themselves is a major concern. In 1972, the nuclear plant inside New York University was threatened to be misused in case the government did not meet the terrorist demands. A few years later, a similar case was to happen on Oak Ridge nuclear plant, where they reached 800 feet close to the plant. However, the day was finally saved. In India last year, a cyber attack case occurred in the nuclear power plant of Kodamkulam, Tamil Nadu. This was a major headline. The NPCIL has confirmed that a lot of data had been stolen. Some suspect that maybe North Korea is involved. However, this is still pretty unconfirmed. This brings us to a very important topic: nuclear security. International Atomic Energy Agency, which is basically the UN's wing to atomic energy, takes nuclear security very seriously. A summit had been conducted in Washington in 2016, which declared that every nation should have at least some body to take care of nuclear power as a security matter. In US, there is National Nuclear Security Administration (NNSA). Russia, the entire Ministry of Defense takes care of it. And in India, there are two organizations, NPCIL and CISF, which stand for Nuclear Power Corporation of India Limited and Central Industrial Security Force.